Hi, everybody. Today's topic, you can see at the top of the page, we're going to add in our last transformation today. You'll see that we're talking about translations of functions, and I think today should be a pretty straightforward day. In fact, I'm going to argue that this is probably what you've got the most background with. So let's go through a real quick kind of Desmos activity. We should be good to be able to hop onto Desmos and pretty freely be able to go through and deal with those 4 functions you see on the right. I'd just like you to go through and put a quick sketch of each one of those. I'm going to to avoid having to write the equations of each of them, how about we go through and we just label each of those with like a certain function notation. So maybe we'll call the first one g of x. We could go this one, maybe f of x. We'll kind of go with our standard. Maybe we go with an h of x for that third function. And maybe the last one, I don't know, we go like a of x. We'll go to the top of the alphabet. That way, all you have to do is just label on your function notation to be able to describe each graph. Okay, you have your base function, y equals x squared. There's our good old parabola. I want you to play around pretty quick with Desmos, put on 4 sketches, and we'll come back when you have those 4 sketched. Okay, pause it now. Okay, and we're back. So let's take a peek at what we should have on our page. So what you should have is something that matches with that. And I just went through and matched up my colors with my labels. I think that just might make it a little bit easier for you to be able to tell those graphs apart pretty quickly. Okay, we should be pretty good on what the effect of adding and subtracting to our function did as a transformation. Okay, the first thing that I want to make sure that we're good at, let's put down our quick kind of big statement. For us, we should recognize that add or subtract caused a certain change in our graph. Really what that was is that means a shift. And we need to know that a shift is a perfectly technically sound term. You can use the word shift, or a little more formal, you can use the word translate or translation. Now, you'll notice that in my vocabulary, I'm going to tend to use the word shift a little more often, just because I think when you say it quickly, translate might get a little mixed up with transform, and I don't want to have that confusion. Transformation, if I transform the graph, that could be any of our transformations up to this point, a stretch, a reflection, or a shift. If I say translate, then that only means a shift. And so I just want to avoid that confusion. However, you are good with either of those terms. The next part that I want to make sure we're good at, and make sure that we get down just that little reminder again with regards to outside versus inside the function. And you're going to see that as we worked our way through, that same pattern continued. That if we were outside the function, affecting the graph outside of it, then our graph was transformed vertically. And if it was affected inside the function, then it was transformed horizontally. Now, you may take a look at it and say, like, I'm having a tough time being able to tell the difference between inside the function or outside the function. And the key for us is to look at the exponent. Our exponent is what dictates our shape. And so if you take a look at the equations of the 4 graphs I gave you, you can see that they're all parabolas. Well, why are they parabolas? Because of the squared. And so now if I change kind of my wording, rather than saying inside versus outside the function, I'm going to say inside versus outside the squared. And now it becomes pretty clear. So notice when we added 4 or when we subtracted 1 on the outside of our squared, our graph was shifted vertically. If we subtracted 2 or we added 3 on the inside of our squared, then our graph was affected horizontally, shifted horizontally. Biggest part that I want us to make sure that we're good, anytime we add or subtract, we should notice that the shape stays the same. That adding a value to a function or subtracting a value before we turn it into the function is going to affect all of our values the exact same way. It's not like a stretch where if we double 1 or we double 1,000,000, those end up being different amounts. As soon as we add or subtract something, all values change the same. Therefore, we are shifting it. The shape stays the same. Now, I mentioned at the very beginning that we probably have the most experience with this. I'm just going to jot something down a little bit because it is something that you have in your background. If you went back to your good old parabola from grade 10, then your vertex form may have looked this way. And in fact, you got really, really good at being able to identify the vertex from the equation of a parabola. So if I was to make it more formal, and now replace my k with a value, I don't know, 4. Replace my h with a value, and maybe I replace it with a -1. Well, then that means that has to change to a +1. And I get rid of my a value out in front, and I replace that with a value. Then you got really good last year at being able to look at that parabola and say, I have my vertex at -1, 4. And we started to just identify properties of a parabola from our equation that we may have moved away from understanding that that was all because it was a transformation from my base function. That when I see that +1 on the inside, I have to recognize that what that does is it actually shifts my graph to the left 1. That when I saw that +4 on the end, I have to recognize that that shifts my graph up 4. And so if we look back onto our black curve, our normal vertex, which occurs at 0, 0, that parabola is shifted. It's just that that parabola now is shifted with its vertex in a certain position. So just in case we kind of moved away from the fact that we've actually addressed these transformations in the past, that might help us out. Okay, what I want to do is I want to jump down to the bottom of that page now, get down some terminology, but also address maybe a big issue in terms of which direction do we shift. So what you have in the middle of the page there, I've given you the equation of a graph, and there's our good old square root function. And all I've asked you to do is just describe how the graph has been translated. Okay, just describe it. So we take a look at the first one, and we should be able to recognize that what's changed in my equation is I've subtracted 5. Okay, we see the subtract, so we know that it is a shift. So I should be able to write down that I have a shift. Now we look at where the subtraction occurred, and we notice that it happened underneath the root. So it happened inside my function. And we know that inside is horizontal. So we know that we're going to shift that left or right. We now just have to examine the direction. And when I see that I have a minus in here, a lot of us last year would have just memorized that that was a shift right. That sometimes we even think about it as almost like, well, it's like my number line, but I just go in the opposite direction. So negatives are left, so I just have to remember when I see a negative, I go right. And we kind of memorize this rule. I hope that we understand that rule. So rather than just writing shift right 5 units, which is 100% correct, that we actually understand why subtracting on the inside really moves that thing to the right. So I'm just going to erase that stuff that I have up in the equation, and I want to make sure that we're good with it. To do that, I'm going to hop into that big blank space that we have down at the bottom. So the first thing that we should be good with is in my original function, my square root we have a couple key points. So for instance, we know that our graph passes through 1, 1. We know it passes through 4, 2. And we also know that it passes through 0, 0. Now, I'm just going to skip over the 0, 0 a little bit because I think some people can get so focused on the 0 aspect that they miss the pattern. So what we're going to do is we're going to start off with the 1, 1. Now, I don't really like my bracket on the left side, so I just want to fix that up. Okay, let's focus in on the 1, 1. What that says then is that when I sub in an x value of 1, then I get a y value of 1, an output of 1. Okay, so what if I now change that equation to an x minus 5? Okay, well now, what is the effect? Well, I should clearly be able to see that if I sub 1 into my equation, I am not going to get an output of 1. If I sub 1 in, then I get the square root of negative 4, and I can't calculate that. And so my key point has changed. Now, through our patterning up above, we know that it's a shift. I don't think that we have to go back and review that. What I want to focus in on, though, is if it is a shift, in what direction? So if it's a shift, and we recognize that it is a horizontal shift because it's inside my function, then that means that my y-coordinate will not change. If I shift something horizontally, my y-coordinate stays the same. It's my x value that's changing. So now what I'm going to kind of ask myself is, what x value would I have to sub in there now in order to get my same y value of 1? So in order to get my y value of 1, then I need to take the square root of 1. Well, what value do I have to sub in that when I subtract 5 from it, I get 1? And our answer should come in pretty quickly on 6. Do a quick check, sub in 6. The square root of 6 minus 5 is the square root of 1. There's our 1. Okay, in one numerical example, we had enough to see that our x value was increased by 5. Now, I don't think we have to go to 4-2, but we could go through that exercise. My focus with us today then is let's make it generic. That let's not just take this key value and think about it, but let's think about all values. And let's look back at our equation. Maybe we can see that because I'm going to subtract 5 from my x before I turn it into my function, before I take the square root of it, then all of my x values have to be 5 greater to get back to what I used to have. Okay? If I'm going to subtract 5 before I turn it into my function, then my x values have to be 5 bigger than what they used to be to get back to my original. Okay, I'm hoping that that generic case makes sense for us. We can now see it in the next key point. That before, I used to have to sub in 4 to get a y value of 2. In my base function, I had to sub in a 4 to be able to take the square root of 4 to get my output of 2. Well, since I'm going to subtract off 5, I have to sub in 5 greater. That means I have to sub in 9 now in order to get my y value of 2. And if I was to ask you, well, where is 9 greater on your x-axis? You should be able to say, to the right. So I'm hoping that that gives us just a general case for why we go in the opposite direction of that operation we see on the inside. So just very quickly, we should be good then that if I was to give you something like the square root of x plus 1, then we can see that what we have on the inside is we are going to make all of our x's 1 bigger than what they used to be. So that means that I only have to sub in x values that are 1 less than what they used to be to get back to the original. since I'm going to add on a 1. And so if I asked you, well, where is 1 less on your number line, we should be good to say that that would be in the left direction. Okay, I'm hoping that that makes sense for us. And even in that context, I want to now extend it to what we dealt with a few times ago. We might now, since we've dealt with our stretch, have a much greater understanding for why, if I have a function f of x, and now I see that I'm going to calculate f of 2x, why that represents a horizontal stretch by a factor of 1/2. Why we have to take the opposite operation aspect to determine our direction. Take a look on the inside. If I am multiplying all of my x's by 2 before I do whatever f says to do, then that means that all my x's only have to be half of what they used to be. And if I make all my x's half of what they used to be, my function gets closer to the y-axis. Conversely, if I had a 1/2 x on the inside of my function, then all of my x's would now have to be double what they used to be, since I'm going to take a half, to be able to get back to my original. So I'm hoping that that gives us some greater understanding. And if not, then at the very least, we can work our way through and say we understand that it's opposite operation. Okay, let's take a look at B then. We should be pretty good to go through quickly and recognize, okay, I can see my square root function, but I'm now adding 2 on outside the function. Well, outside is vertical. Some people would write this. So it's a vertical shift. Okay, clearly a vertical shift isn't good enough. You have to give me the direction, up or down. We see that we're adding 2 to the outside, so that's just me adding 2 to my y values. So that means up 2 units. Okay, now I hope that you can see that what I've written in red is redundant. And I'm hoping that we're good with the term redundant. If you want to think of that, you can say that it's not needed. Okay, it's already been stated. I want you to take a look at that sentence because a ton of people write it and I need you to stop. Don't tell me a vertical shift and then tell me up. Since you have to give me the direction, which means you gotta tell me up, then don't write in vertical. Like you can't vertically shift something left. So as soon as you say shift up, then we know it is a vertical shift. Okay, let's make sure that we're not being redundant with our statements. Okay, let's take a look at C. C, we see that we can have 2 transformations. So maybe I take a look at that shift underneath my square root. I see that I have a -2 underneath there. So I know that I need to shift that curve to the right 2 units. And at the same time, I see that I have the +4 on the end, up 4 units. Now, I hope that we're good, that we can picture in our minds that if I was to take any graph and shift it right, then up, I would get to the exact same position as if I shifted it up, then right. That the order of my shifts do not matter. Okay, very quickly on the last one, we should be able to get some confirmation. It's more just the time it takes to write it down. We should be able to recognize that we have a shift because we have add or subtract in there. I have the +3 underneath, so that means that I have to shift it left 3 units. And at the same time, I see that I have my -1 on the outside. There is a down 1 unit. And there we go. So I think we've addressed a ton of stuff on that slide, and I think we should be good to actually go through and deal with some of our transformations. Okay, let's jump onto the back of that page. Okay, at the top of that page now, I just want you to get used to working with generic function notation. So what you'll notice is now I've removed the square root. Some of you will actually find it easier since I removed the square root because it makes it a little more explicit to you of what's inside versus outside the function. I'd like you now to go ahead and answer all 4 of those functions. Describe how the graph would change given those new notations. Okay? Pause it now. Okay, we are back. So within that first one, we notice that we have a +2 and it's on the inside. The plus tells me shift. The +2 now tells me that I'm shifting it left 2 units. So hopefully we match up. You take a look at B, and you notice in B, we are adding or subtracting. We see the subtracting, so that means I have a shift. That subtraction is happening outside the f of x, so it's vertical, so I'm shifting down 3 units. We take a look at C. In C, we notice that we have 2 add and subtracts. Doesn't matter what order, I go through and deal with an add or subtract. So maybe I deal with the -4, and I say I have a shift 4 units. Now I need my direction on. It's minus on the inside, so everything has to be bigger. So that means to the right. And I have to deal with my +1 on the end. That's outside the function, so that's vertical. And 1 unit up. And now we take a look at D, and just so that we're all good, maybe I choose to deal with that vertical shift on the end. I can see that I'm going to shift down 2 units from the -2 on the outside of the function, and then I can deal with the +1 on the inside. That would be a shift left 1 unit. So hopefully we match up with those 4. Now what we're going to do is we're just going to quickly go through and graph each of those. So we've spent some time working through our common functions, the functions we'll be responsible for. I wanted to throw something at you that you wouldn't know the equation to. So take a look at the bottom of that page. What I want you to do is I want you to take all the notations that we have up top, and we're going to go through and we're going to produce those graphs down below. So I'm going to take the function in A, y equals f of x plus 2, and I'm going to produce the graph of that on that grid. Question B said y equals f of x minus 3, so that's going to be problem B. Because what you've been told is on each one of those sets of axes, that is the graph of f. So I just want you to take your time, pause the video, go through, and produce those 4 graphs that match the notation from above. Okay, pause it now. Okay, we're back. So we've already interpreted what that +2 on the inside means. We know that we have to shift that left. I just want to go through a couple expectations for us when we graph. So the first thing I think I want you to notice is we recognize that our shape is made up from a series of line segments. So since we're going to shift it, the shape doesn't change. That means our transformed graph is going to have a series of line segments. The easiest thing to do is to go and transform all your key points. And in most cases, key points become changes of direction. So I could take all of these points that I'm putting an X on, and if I transform those points and then just connect them in the same pattern, then I have my graph. So I'm going to erase all that, and now I'm just going to go through and I'm going to transform my points. Okay, let's take a look at this first point that I've put my X on. My new function tells me to shift that to the left 2. And I notice that if I shift that to the left 2, I am off my grid. Do not go and mark that point as an estimate off your grid and connect it. No. If you're given a grid to produce a graph on, then you graph that function on the grid provided, not off of it. Now, it doesn't mean that I completely ignore the fact that I can't graph that. Like I can think, hey, I know that I've got that point out there by that dot, but I can't graph to there. So all that means is I have to go to like my next key point. And if I go to that key point, then what I'm going to do is I'm going to shift it to the left 2. Take my next key point, shift it to the left 2. Take my next key point to the left 2. My last key point to the left 2. And now I'm going to connect them in the same order. Okay. All of the points that I can connect that are on my grid are nice and easy. So I can connect there. I can connect there. And I can connect here. And you notice that when I connect those points, my shape doesn't change. It's good. However, I have to be very careful that when I go to connect and draw that last line segment, I don't have that other point to connect it to. So I need to recognize that shifts do not change the shape, and shape talks about slope. So as I go through to draw on my last line segment, I need to make sure that it matches up with the slope of the red line segment that I've just highlighted. So I need to make sure when I now put this on that I am trying to draw a parallel line to that. So I'm going off my grid. I'm not even focused on that point. I graph my graph to the edge of my grid and I stop. There we go. So if you've given me that blue graph, looks great. Okay, I think that was the only thing that we needed to really talk about. I think for the rest of it, we should be good. The only last thing that I want to mention is you'll notice that I transformed all of my key points first, then I connected. Some of you may struggle as we get into more and more transformations being done on a single graph to be able to connect them in the proper order. Things are going to get reflected and stretched and shifted, and that maybe what I might recommend is connect your points as you transform them. So if there was anybody who had an issue on that blue graph, then I'm going to go through and I'm going to produce a purple one for question B. That maybe what I do is I say, okay, I'm shifting down 3. My first key point gets shifted down. My next key point gets shifted down. And to avoid any confusion about how I connect these, I'm going to connect them as I go. Now I can transform the next key point, connect them. Transform the next key point, connect them. Transform the last key point, connect it. And we should end up seeing then that we have our same shape shifted down 3 units. Okay? So if you needed to make any adjustments based on what we've talked about, then make those now, pause the video. But otherwise, we're just going to confirm our last 2 graphs. Okay, we're back. And what you see on the screen then is your last 2 graphs. There is question C, and there is function D. You'll notice that in C, a part of my graph was off my grid, so I had to make sure that the portion I'm highlighting right now in purple was parallel as best as I could judge with that last line segment. And then it was nice, and D all fit on my grid, so I was able to go through and transform those. Okay, I'm hoping that today's stuff was a relatively quick review, maybe even, of translations or shifts. And I'm hoping that we can see how it now applies to generic functions, not just parabolas from our previous year. Okay, same thing as normal. Jump in, get some practice, because the next time we get together, we're going to be throwing all of these transformations together. Okay, good luck.